right, so next up we have Dr. V. And so Dr. V, a researcher and an engineer, has come to join us today to create a connection to technology in your brain. Let's welcome her on stage. Thank you.
Good evening, everyone. I'm very excited to tell you a little bit about how electronics can help us understand the brain. Now you'll have to wait between every slide. All right. Who has heard about Moore's Law? Does anybody know Moore's Law? Okay, a couple of people. All right, so Moore's Law in the field of electronics, or more specifically in the semiconductor industry, basically describes that our computers are becoming more powerful over time. So this graph shows that due to a couple of innovations in the field of electronics, we have seen an increase in calculations per second that a computer can do per spent dollar. And especially when you look at in the 70s, there was the invention of the integrated circuit, and that led to suddenly now a 1 billion-fold improvement in our computer performance. So what does that mean in daily life? So if you look at computers in the 50s, they were taking up an entire room, so they were huge instrumentation. They had a cost of current dollars 7 million, and they used centimeter-sized switches. And this huge computer could only do 5,000 operations per second. Whereas a smartphone, so compared to this computer, the smartphone that you have in your pocket is a supercomputer. It only costs about $700 US. And the basic technology that is inside of it is using switches that are now only around 5 nanometers size. And that is the same as 2 DNA strands. So very small features in there. And this device can now do 11 trillion operations per second. So this is also known as 11 teraflops. So a tremendous increase in functionality per dollar spent, and giving you the possibility to do amazing things with a small device in your pocket. But make no mistake, we still develop computers that take up entire rooms. So the most powerful supercomputer at this moment is located in Oak Ridge National Laboratory. It's called the Frontier supercomputer. And this computer can do exaflops. So that is a 1 with 18 zeros, and it uses 20 megawatts of power to do so. You might start to wonder, why is she talking about all of this? Because we came here to learn about the brain. And I'm here to tell you that our brain can also do exaflops of operations, and it only uses 20 watts of power. So your brain is 1 million times more energy efficient than the best supercomputer in the world. And that makes you think a little bit. Do you ever wonder how much energy you use when you ask Google a question? When you ask Google a question, you use 0.3 kilowatt per request. If you ask ChatGPT a question, suddenly it's estimated that you use 10 times as much energy, about 3 watt hours per request. And you might have noticed that if you enter a question into Google lately, there's like, on the top, you have an AI-generated answer that came in recently. That is AI-powered Google search, and it's estimated to lead to a 30-fold increase in energy that you need for this to give you an answer to your question. So all of us, even without a choice, we have increased our energy need tremendously by doing Google searches. And if we calculate this on a yearly basis, we are now using more power to power the servers and the data centers to enable this than all of the residents in the entire state of Massachusetts on a yearly basis. That's mind-blowing, right? All right, so maybe next time you can consider asking your own brain a question or your friend's brain and save a little bit of energy. Make sense? Okay, so now that we've established that we have this wonderful computer in our body that is also very energy efficient, obviously our brain also has its limitations. So definitely with age, as we've heard in the previous presentation, we do lose some of our capabilities and performance with aging. And neurodegenerative diseases are a huge burden on our society. With the aging population, we actually now have 1 in 3 seniors dying with some form of dementia. And 3/4 of those people are not properly diagnosed, let alone that they are getting the care and the treatment that they need. And it is estimated that by 2030, the cost worldwide to our society will be about $2.8 trillion US. So this is something we really need to spend our time in studying. So I'm really happy with this event and getting you all excited about neuroscience, because it's so important to better understand these diseases and then try to prevent them and develop better treatments for it. So now you have to think back to my first slide when I asked about Moore's law. So in drug development, there's actually an opposite law that is called Reumers law. And so whereas Moore's law says computing becomes faster and less expensive over time, in drug development, unfortunately, we see the opposite. Drug discovery is becoming slower and more expensive over time. And so there's a couple of explanations for this. Some diseases are poorly understood, the mechanism poorly understood, so it's also difficult to know the target that you're developing a drug for. And specifically, drug safety is becoming more expensive, drug safety testing, so slower and more expensive to test these drugs for how safe they are. And specifically in neuroscience, the delivery of the drug to your brain is also especially challenging, because we all have something that is called the blood-brain barrier, and this barrier is extremely good in keeping toxins and dangerous stuff out of your brain, but it puts a difficult challenge on drug development to get the drug into the tissue where it needs to act at the right dose. So specifically in neuroscience, that is a problem, and we are trying to use animal models to predict a little bit better how all of this is happening, but animal models really poorly reflect human physiology, and obviously there are ethical concerns and high costs related to that. So maybe we can learn from electronics and translate some of that improvement to our medical research and drug discovery. Or we can use the electronic chips to better understand disease and help us in drug development. So I'm really happy that Dr. Lu already introduced Parkinson's disease to you, so that saves me a little bit of time. But there are specifically a couple of challenges with understanding Parkinson's disease. So one is there are diverse causes for the disease, not only genetic factors, but also environmental factors. So there's a lot of variability in this patient population. Secondly, if you want to study the disease, you want to have access to the tissue, and typically you only have access to the brain once the patient had passed away, so that you can do what is called post-mortem analysis. So there is really no opportunity to look at the dynamics of the disease, because you only see the endpoint when the person has been sick for a long time. And many of the specific brain regions involved in the disease have been heavily affected, damaged, or the cells have already died, so you cannot study it in this endpoint tissue. And thirdly, we can, as I mentioned, we can use animal models, but these animal models don't reflect, they are living organisms, so what we call in vivo, but they're not human, so they don't reflect the human physiology very well. And if we want to take cells out of the human body, now the sample is human, but it's not in a living organism, so not in vivo. So we need better models to study this disease. And one solution there is that we can try to build a human, so physiologically relevant brain circuit. That means that you're in a dish, in a plastic dish, building a model for the disease. And so Dr. Lu already mentioned there's a couple of specific brain regions involved in Parkinson's disease. And there are neurons, highly specialized neurons in all these regions that are communicating with each other. So they need to influence each other to initiate movement, to stop the tremble. And so what we could do is build the circuit in a dish. So the hypothesis is if we can study how the communication between these different regions is affected, can we see electrical fingerprints that are really specific for the patient population and maybe even subpopulations. Instead of looking at the group of people as one and the same patient population, maybe we'll see differences and understand a little bit better what is happening in different patients. So how do we plan to do this? There is a process called induced pluripotent stem cells. So what you need to do is you take skin cells or fibroblasts from a patient or a healthy person, and we can actually de-differentiate these skin cells into stem cells. And as you know, stem cells have the potential to become different types of cells. So then we use another protocol to then differentiate again these cells into specific specialized neuronal cell types. And they reflect the cells that you find in those different brain regions that are involved in Parkinson's disease. And if we put them together in a dish, they will connect with each other and they'll start talking to each other. So they'll start communicating, and we can study that. And in the bottom right, you see a picture of what this looks like in a dish. So these are the different specific neuronal cells that are connecting to each other and start communicating with each other. Now you have to think back to the cell phone that I showed you. And if you remembered, I explained that the switches in there are actually the size of 2 DNA strands. And the point I wanted to make there is that semiconductor technology in size and scale is coming really close to the scale of biology. So what you see here are neurons growing on the surface of a CMOS chip. And the little squares that you can see everywhere, we call them electrodes, but they act like microphones, little microphones. And I told you that these cells communicate with each other through electrical signals, and those microphones can actually pick up the chatter. They will listen to the neurons talking to each other. So now, if we take that circuit, the cells communicating with each other, and we grow it on top of the chip surface, we can listen in to how these cells are talking to each other. And we can compare healthy circuitry with diseased circuitry and subtypes of these cases. So we will build those specific electrophysiological fingerprints that I was mentioning earlier. And so this is all with the goal to look at a group of patients, take their cells, really study the individual differences. You could even do that for the sex differences, like we heard earlier, male versus female patients, and see what is going wrong in that communication between the different cells, define the disease signatures, and then subdivide these patients in subgroups, better understand the mechanism, and develop and test different treatments for these populations. So then you get to a situation where you can do personalized therapies. So to end, I want to take this one step further into space. So it's very well known that space offers an environment of accelerated aging. You might have heard of astronauts losing muscle tissue or having other symptoms of accelerated aging while they spend time in space. So this is known as a very nice research environment to study aging. And you might not know this, but if you want to do research in space, you're very limited by what you can send up there. So you have to build a technology or a research system that is very small, so compact. It needs to be lightweight, and it cannot use a whole lot of energy because there's a lot of things going on in there. So again, the power of electronics is that you can really reduce these really bulky equipments and build a small research instrument. So on the bottom right, you see how we really built a little research experiment, and it's only the size of a shoebox. And this shoebox went on a Blue Origin rocket into space. What we used was a smaller version of our microphone array in the shape of a needle. That needle is actually thinner than a human hair. And we inserted in a 3D neuronal cell culture. So now with this small equipment, we can listen to neurons in space and study how the communication between these neurons is changing over time. So with that, I hope I convinced you of the power of electronics to study and understand our brain. And with that, I thank you all for your attention.